Good morning. So today I will continue the lecture on modes of fragmentation and mass spectrometry. So we have discussed yesterday about in the last class about the modes of fragmentation, principle of mass spectroscopy, etc. So today I'll take up this. I'll continue the modes of fragmentation and mass spectrometry. So we have different types of modes of fragmentation. So we have discussed in the last class. First one is the fragmentation. So first one is fragmentation at adjacent to the branching point. Okay. So this one. First one is adjacent fragmentation adjacent to the branching point. This one we have discussed this earlier that for the long chain hydrocarbons having branching point, so branching takes place at the branching point where the longer chain, longer fraction will go as compared to the lower fraction. Okay, like this to give the more stable carbocation. So we have discussed this one. And second one is the fragmentation due to loss of fragmentation due to loss of small stable molecules. So like we have discussed in the last class about like molecule like water, ammonia, carbon monoxide, carbon dioxide, ethylene like this. So for example, say in the alcohols, mostly we got lost, water are lost. So from alcohol, waters are lost. Okay, the pair molecule. So water are lost. So molecular ion is mostly this one. So we got a fraction to contain this one. That is M-18. So like this. So we have discussed. So if we for alcohol, we go found a peak at M-18, M minus water. Okay. So you have discussed this one. So this is the loss of small stable molecules like water. In the case of amines, we got ammonia are lost, and generally primary amines lost as ammonia. The third one is fragmentation. Due to stable carbocation. More stable carbocation. So this one fragmentation to give more stable carbocation will give the higher base peak or higher intensity value. They will give the higher intensity value in the mass spectrum. So having more stable carbocation means more resonance structure will give the more stable carbocation. So we have discussed this also in the last class. Okay, these are the three. Then another one, fourth one is fragmentation by loss of fragmentation by movement, or you can say by movement of one electron. Okay, by movement of one electron. This is you can see the arrow like the piece of arrow, movement of one electron. So fragmentation can take place like this also. And for fifth one is fragmentation by movement of two electrons, by movement of two electrons. So this is very common. This one is very common system. Okay. So by movement of two, this is normal arrow type. So this also we have discussed earlier on. Say. So these are, and last one is sixth one is. So you cannot see this one. Okay, sixth one is fragmentation by elimination of by multiple sigma bonds. Okay. Sixth one is elimination fragmentation due to elimination by multiple by multiple sigma bonds. Okay. This one also we have discussed is like example like this heterogeneous reactions. This one. So when you go to bombarded with electron, this one, okay, this one molecule bombarded with a high electron energy, then you get a molecular ion peak, and then this can undergo fermentation. So like the 2 electron system or 1 electron system, you can have 2 electron system. So fermentation takes place. So you got this one go like this is in the 3. So like this. So you have plus nature molecules like like this. So the fermentation takes place. So multiple rupture of multiple sigma bonds. So one sigma bond is broken here, another one is broken here. So this is another fermentation due to elimination of multiple sigma bonds. So the last we have seen next week. Today we'll discuss more in detail about the fermentation due to fragmentation due to McLaughlin rearrangement. Okay, fermentation due to McLaughlin rearrangement. McLaughlin rearrangement. Okay, rearrangement. So yeah, this is very common. This is very important. So it gives a very good, a bit high intensity peak given in the mass spectrum when and there is a compounds which can undergo fermentation due to McLaughlin rearrangement. Then they can give high energy, I mean high intensity peak. They will give. And the third one is the last one is the fermentation due to nitrogen rule. Okay, fermentation can take place due to nitrogen rule. Nitrogen rule. So this also we'll discuss this thing. Okay. Last class we have discussed up to the 6th one. So now today we'll discuss fermentation due to McLaughlin rearrangement. Today another fermentation due to nitrogen rule. These two we'll discuss. Okay, these two. Today we'll discuss these two: fermentation due to McLaughlin rearrangement and fermentation due to nitrogen rule. So let's light on here. So you know that what is the McLaughlin rearrangement? So you might be knowing what is the. Let's come to fermentation due to McLaughlin double F rearrangement. Okay. So here to know what do you mean by what is this McLaughlin rearrangement? What is McLaughlin rearrangement? So we have to discuss what is this McLaughlin rearrangement is that migration of gamma hydrogen atom followed by cleavage of the beta bond. Okay, any compound having gamma hydrogen atom, they can undergo rearrangement to give followed by the cleavage of the beta bond. So for example, say I write on here McLaughlin involves McLaughlin rearrangement involves the migration of gamma hydrogen atom. Can you see this one? Hydrogen atom. Migration atom followed by the cleavage of a beta bond, CC carbon bond, or like that. So say, for example, I will give one example. Okay, let's say the hydrogen here is R. Okay, any long chain or thing like that. Then you can have let's say some other ketone or like a ketone carbon group or R prime. Alpha, beta, gamma. This is alpha position, beta position, and gamma position. Okay. So we have this type of compound, and the ketone very longer than ketone. Then some undergo migrations. Gamma hydrogen is migrated here. Then this beta bond, alpha beta bond is cleavage. Okay, CC bond is cleavage take place followed by. So we got a neutral molecules. This one is R here. Gamma this is broken down here. Plus we got this OH. Okay, hydrogen is migrated to alcohol gives. So this type of rearrangement is known as Magley-Fertig rearrangement. So here I am repeating again. Magley-Fertig rearrangement involves the migration of gamma hydrogen electron followed by the cleavage of the beta bond, beta carbon-carbon bond, alpha beta bond. So to go to this compound. So here I am giving one example from ketone to conversion to alcohol. Okay. So this is known as Magley-Fertig rearrangement. This Magley-Fertig rearrangement can be applied to mass spectrometry or by fermentation. So fermentation can take place like this. So here actually Magley-Fertig rearrangement undergoes mostly in ketones, aldehydes, long chain aldehydes, ketones, and amines, and then unsaturated compounds, even unsaturated aromatic compounds like this. So this Magley-Fertig rearrangement can be found in can undergo in compounds like in many compounds such as long chain ketones, carbonic compounds, ketones, aldehydes, and these amines, long chain. They are mostly long chain having gamma hydrogen atom. If they have gamma hydrogen atom, they can undergo this rearrangement. Unsaturated compounds, aromatic compounds, aromatic hydrocarbons, also aromatic hydrocarbons, etc. Okay, so these are they can undergo this type of Magley-Fertig rearrangement. So this Magley-Fertig rearrangement can be applied to mass spectrometry, so undergo fermentation. So let us see the one example. Okay, I'll give the one example here. So the two, which is butanol, this alcohol, this ketone, say CH3, CH2, hydrogen here, then we have CH2, then CH2, then we have this aldehyde here. Okay, let's say the 1, 2, 3, 4. This is butanol. Okay, this butanol, the aldehyde. Okay, this butanol can undergo Magley-Fertig rearrangement. So first, bombard this with a high energy electrons. This natural molecule bombarded with high energy electron. We got a molecular ion. Okay, this first parent ion is got. So this parent ion can undergo rearrangement. This butanol can undergo rearrangement in mass spectrometry. So here, by Magley-Fertig rearrangement, so first migration takes place like this, then go this way, and then like this cleavage takes place. Beta bond is cleavage. Hydrogen migrating. This is alpha, beta, and gamma here. Okay. So gamma hydrogen is migrated. Migration takes place with the cleavage of the alpha beta bond, carbon-carbon bond. So here we got a CH2, double bond CH2, and then we got this plus this CH2, double bond C, OH. Okay. This one. So we got another M by Z value. So this type of rearrangement fermentation can undergo in the mass spectrometry. So we can even I will give another example for aromatic compounds here. Okay, aromatic compounds. So benzene, CH2 here, then the alpha, beta, then we have hydrogen here. Okay, alpha, beta, gamma hydrogen here, gamma. So you can have RR here, something like that. Okay, you can write this. Here also same case, it's done here. This migration takes place. Hydrogen migrated and is broken down. This beta bond is broken down here. Alpha, beta, gamma. So gamma hydrogen is migrated. After getting this molecular ion bombarded with high energy electron, then we got molecular ion, M plus ion, then undergo fermentation by Magley-Fertig rearrangement. So we got this compound. Is two hydrogen here, one hydrogen here, and hydrogen here. So here we got this one plus this double bond. Okay, so just like this we can have. So here I am giving the example by movement of two electrons, but you can undergo by one single electron also. You can undergo by one electron system also. So Magley-Fertig rearrangement can be this also. What I am telling you that parameters can undergo by Magley-Ford rearrangement. So it can be applied for differentiation of two similar compounds also. So I'm giving here, for example, so Magley-Ford rearrangement can get differentiate two compounds having two isomers, having same molecular mass and having same molecular formula. So for example, say 3-methyl 2-butanol, 3-methyl 2-butanol, okay, 2-butanol, ketone, okay, 2-butanol and 2-pentanol, 2-pentanol. So to have compare this, you can compare these two molecules, differentiate these two molecules by mass spectrometer, mass spectrum, by using this Magley-Ford rearrangement. So here 3-methyl 2-butanol, 1, okay, CH3, C, CO, CH3. So 1 here, 1, 2-butanol, 2 ketone here, and 3-methyl 1 to 3-methyl group here, and 1 hydrogen here. Okay, this is the 3-methyl 1 to 3-methyl 2-butanol, and here CH3, CH2, CH2, CO, CH3. This is the 2-pentanol, 1, 2, 3, 4, 5, 2-pentanol. So they have same molecular formula, same molecular mass, same molecular mass, 86, and molecular mass is same, okay, 86 molecular mass. Here also same molecular mass, 86, and there also the molecular formula also same, C5 is, the molecular mass is C5 is how many? 7, 8, 9, 10, 11. C5 is 11. Oh, okay. 1, 2, 3, 4, 5, 6, 7, 8, 6, 7, 8, 9, 10. Okay, 10 here. Okay, 10. Here also 1, 2, 3, 4, 5. C5 is 5 is 10. Oh, okay. Same molecular formula. Molecular formula is same. So they are isomers. So we can differentiate these two compounds by Magley-Ford rearrangement. So in this case, there is no alpha, beta, no, there is no gamma hydrogen. So you can undergo Magley-Ford rearrangement. But here, 2-pentanol have alpha, beta, gamma. So you have one gamma hydrogen atom. So you can undergo fragmentation due to the Magley-Ford rearrangement. But here, it doesn't go Magley-Ford rearrangement because it doesn't have gamma hydrogen atom. So I showed one fragmentation for this compound 2-pentanol. 2-pentanol, so let's say CH2, okay, the hydrogen here, and CH2, then CH2, then this carbon group, and CH3. So this is 2-pentanol, okay. This is 2-pentanol. So after bombardment with a high energy electron, so we got a pass, we got that. This one, so we got this one, and this one, okay. So we have this one bombarded with high energy electrons. So we got another one electron is knocked out from here. So one electron is knocked out. Right. So let's say one electron knocked out from here. CH2, hydrogen here, CH2, CH2, CO, CH3. So let's say one electron is knocked out in positive charge here. This okay, let's say. Okay. Now, so this is the molecular ion, M plus ion. So they undergo migration now. This one electron goes here. Another electron. I'm giving the this energy electron system. Okay. So one energy here. So like this. So we got here. Then this can go again. This pass, okay, fermentation pass. I will write down here. It is not coming. So the 2-pentanol, 2-methanol. So you got migration pass. So here you got this one, CH2. Okay, electron, and then the CH2, CH2, C. So here O, CH3. Now this one has gone. This also it comes hydrogen here. So the positive charge here. Okay. So now positive charge and two electrons are here. So I can write these two positive Okay, so again this undergo rearrangement, this can go this and then go another this one, then this one, so this one like this. Fermentation takes place. This is a mechanism. I am giving the mechanism. So here lost this one. So here, okay, here I'll show you. This one will be lost. Okay, this one will come. So here these two will come. This one electron combined with another electron. So here, so combine now she's to both double bond will come. Okay, this will come. Now I'll show you this wave is like this. Not 2 arrow and 1 arrow, single arrow. Okay. So here, so you got a CH2 here, H2C double bond CH2 here, then plus this becomes CH2 radical and C double bond O, positive hydrogen here, this positive charge, then CH3 here. Okay, this CH3. So now this one, we got this one, even cation radical, so here cation radical, so here cation radical. So bombardment molecular ampere. Now this also you can get positive charge in the carbon also here. You can have positive charge in the carbon. So the isomeric form. Okay. So you can have this. So you have positive charge in the carbon, then CH2, then C, OH. Okay, OH. Now it becomes 2 electrons are here, positive charge, 2 electrons. Now 2 electrons are given, so you can have like this CH3. Now this carbon becomes positive charge. Okay, so here is radical, cation radical. So you can write all this structure, you can together write this formula, right? You can write CH2, H2C, no, COH, OH, double bond, you can write double bond OH or like this. Then CH3 like this. Okay, so this way you can write also. Okay, this way plus this is the m by z value you can have. So this is the way how mechanism I'm giving. Then this is the formula you can write this way also. This is a mess. So in the 2 pentanol can give fragmentation. One fragmentation is having m by z value about 50 IOK. But this one, this type of this fragmentation, fragment ions cannot be can be found in the 3-methyl-2-pentanol, the earlier molecules, but it is found in the 2-pentanol. So I can comparing this by differentiating these two. We can say they are having different mass spectrum. So I'll show the mass spectrum how it goes. In the case of 3-methyl-2-pentanol, there is no so mass spectrum. Okay, mass spectrum of gaseous keeping. Okay, so here 0 to 100 relative evidence versus m by z value. Okay, so you can have 0 to 50. Okay, 50 like this, and then here we can have 10, 20, 10. Okay, 20. Then 30, 40, 50, 60, 70, 80 like this, 90, 95, 100, okay, 85, 86, 100, 100. Okay, here. So in the case of the fermentation of this 3-methylbutene, here I'm showing what a 3-methylbutene. So here 86 will come. 85 is slightly in here. Okay, 86. Then 43 will be the highest peak. 43 will be the base value. Okay, 43. Then we have 71, 60, 71, 71 slightly like this. C5 is 11, C3 is 11, another one 41 here, 41 small one here, then 27 is slightly here, small, okay, slightly, okay. So like this we got. So these are the mass spectrum of 2-methyl 3-methyl 2-butanol. 2-butanol, okay. So this one C3, CH3, and then okay, 3-methyl 2-butanol. It's mass spectrum of this one. And in the case of similarly, in the case of 2-pentanol. So here, you can see this one. Okay, so the same value and by the value and this one, but here they do the peak. See, almost are same. Almost same. Our peaks are almost same. 21, 27 also, 27 also here, 26. Okay, all the same. But yeah, another one in this case, and 58, there's an intensity peak, 58, and others are same, 86. Okay, so here 80, 90, 60, and 40, then 30, okay, 40, 10, 20, 10, 30. So here 0 to 100. Array relativity abundance, and this one is for M by Z value. Okay, so here is for 2-pentanol. This is 2-pentanol, and then one is 3-methyl 2-butanol. Okay, so here in the we compare this to here. One peak is here M by Z 58 due to the McLafferty rearrangement. Other side 86. 86 is for M by Z. 86 is molecular peak, and another one is M by Z 57, M by Z 71, M by Z 71 is C5H11 cation, and M by Z 43 is 43 C3H7, and there's another 41 here, M by Z value another one 27. Okay, 41, 27, 43, another 57 here, and 71 here. Okay, this one we got this 86, M by Z value 86. So all the peaks are same, but here in the case of 2-pentanol we got a M by Z value 58. This is due to the McLafferty rearrangement. So by comparing these two, we can say that these two, one is a 2-pentanol, another one is 3-methyl 2-butyl, okay, 2-butanol. So by this way we can compare these two. So I'm giving, so by the McLafferty rearrangement we can differentiate two compounds having same molecular mass and more molecular formula by using the McLafferty rearrangement. So you have an extra peak will come in the case of 2-pentanol, there is a gamma hydrogen atom, but in the case of 3-methyl 2-butanol, there is no gamma hydrogen, so there is no McLafferty rearrangement. So let's come to the fermentation due to last one, fermentation due to nitrogen rule. So let's come to fermentation due to nitrogen rule. Fermentation, this is the last one. Okay, fermentation due to nitrogen rule. Nitrogen rule. So this is 8. Okay, I think so. It is 8. Okay. Nitrogen rules states that this rule states that any compounds containing an even number of nitrogen atoms or no nitrogen atom, that is 0, will give a molecular ion with an even mass number. Now that I will write down here. My nitrogen rule states that compounds containing an even number of nitrogen atom or no nitrogen atom. There is 0 in even number. There is 0 in even number. Okay, even number. That means if there is no nitrogen atom or even number of nitrogen atom, then then we'll give a molecular ion, the M plus ion, okay, with an even number, mass number means you can say even mass number, or you can say M by Z value, mass number or even M by Z. Okay. So I will repeating again. The nitrogen rule states that the compounds containing an even number of nitrogen atom or no nitrogen atom, then they will give a molecular ion with an even mass number. Say for example, say CH4 methane. Okay. So when you methane doesn't have any nitrogen atom, so it is 0 even number. So this is even number. So this mass number is 16. So when you bombard it with high energy electron, it gives a mass M by Z value is 16. So even number. So even. Similarly, when there is nitrogen atom, similarly we have, say, let's say one having with nitrogen atom having say NH2 hydrogen. Okay, let us say hydrogen NH2. So when you bombard it high energy electrons, so you got NH2. Okay. So here M by Z value is also here 28 plus 32. Okay, here 32. Okay, 28, 30, 32. Okay, so what I'm telling is that even number nitrogen atom will give even number M by Z value in the molecular ion peak. I'm talking about the molecular ion. Okay, so molecular ion, they will have, if the even number will give, or no nitrogen atom, even number nitrogen atom will give the even number of even mass number or even value of mass M by Z value even mass. Suppose similarly odd number of nitrogen atom. Similarly, odd number of nitrogen atom causes the molecular ion to give the odd number mass number. So similarly, if there is odd number of, an odd number of nitrogen atom. Odd number of nitrogen atom causes the molecular ion to have an odd mass number, or you can say odd mass number, or you can say mass number, or you can say M by Z value. Okay, mass M by Z value. So what nitrogen atom will give odd mass number in the molecular ion peak. So for example, here also many are ammonia. So we'll give bombardment, will give M by Z value how much? 14 to 17. Okay, 17, and this is ethylamine C2H5 NH2. So there is odd number of nitrogen atom here, only one nitrogen atom. So when you bombard it, you got a molecular ion. This molecular ion by Z value, how much was 24, 29, and then 45. Okay. So here we got from odd number of nitrogen atom will give odd M by Z value or number. So they generally called nitrogen room. This is only applied for molecular ion. So what I'm telling you, molecular ion. So it can be applied to other fragment ion also. So it can not only to the M plus ion. So M plus ion, when you this fragment, you have mass M by Z value is odd. Okay. So then when you lost one, when you undergo another fraction fermentation, then we get M by Z will be even number. Okay, even number. Or M by molecular ion after fermentation with a single fermentation will give even number of the fragment ion. Okay. So or in the case of even molecular ion will give more fragment ion after fermentation, okay, by single point. So what I'm telling you, when the molecular ion, say they have even molecular ion, even M by Z value of molecular ion peak. When you undergo fermentation, they will give odd M by Z fragment ions. Okay, fragment ions. After one fragmentation, single fragmentation. Similarly, odd M by Z value of M will give even M by Z value of fragment ions after fragmentation. So that means not only the nitrogen rule can be also applied to other fragment ions. So I'm writing here this one. So in another way we can write this n odd number on n odd electron ion on n odd electron ion. It is here that M by Z value that ion will be at even here even mass number or even M by Z value mass number if it contains an even number of nitrogen atom and even number of nitrogen atoms. Okay. So here we can apply for knowledge to the molecular ion. An odd electron will be at even mass number if it contains an even number of nitrogen atoms. Okay. In the same way, similarly, in the same way, an even electron, so like this, even M by Z value, even electron ion, and odd electron ion here, even electron ion will with an even number of nitrogen atoms, with an even number of nitrogen atoms will appear an odd number and will appear an odd mass number. Okay, mass number you can say M by Z value. This is opposite. Okay, so an odd electron ion will be at my even mass number M by Z value if it contains even number of nitrogen atoms, like earlier one that hydrogen hydride and S4. When you got a molecular ion peak here, M by Z value is 32. It's not 32. When you bombard this one again, when you lost one fragmentation into S3, then you come to odd. So example here, okay, hydrogen hydride into S4, NH2, okay, like that, NH2. Okay, you got a molecular ion peak, M by Z value is 32. So here, when you undergo fragmentation, so we lost one here at the decay, then you get NH2 positive. Okay, so here by Z will be 31. So here an even electron ion with an even number of nitrogen atom. If there is a nitrogen atom also even there. What will have two nitrogen atom even number. So this will give an odd mass number, odd M by Z. Even will give odd, and odd will give mass, even number if they have contain even number of nitrogen atom. So what I'm telling you, so it is a nitrogen rule. Nitrogen rule, for simply you can say, first one is that nitrogen rule says that I'm right on. Okay, for molecular ion peak, even number. I'm writing down again. Okay. So first one is that even number nitrogen atom, even number of nitrogen atoms, or no nitrogen atoms, or no nitrogen atom after bombardment with the high electron. This is for making this to give. They will give molecular ion having even mass number. Okay, even M by Z value. Okay, if they have contain even nitrogen atoms. Okay, after bombardment they will give, and odd will give odd number of nitrogen atoms. After bombardment they will give a molecular ion peak with set even odd M by Z value. Okay, so this is first case. So here, even this in the second case, this is only apply for molecular ion, but you can apply for other fragment ions. Okay, other fragment ions, you can say that n odd equal that or even number of even electron ion will with any even number of with even number of nitrogen atoms. Okay, nitrogen atoms, they will give even will give odd mass number, odd fragment ions, okay, fragment ion. That is their fragment ion will be, that means their M by Z value will be odd M by Z value. Fragment ion will be M by Z value will be odd. Okay, so even electron ion with even number of electron atom will give fragment ion we having odd M by Z value. Similarly, say odd electron ion with even mass number, even number of nitrogen atoms. So we'll give after bombardment, and mass fragment another fragment ions will give a fragment ion having even M by Z value. Okay. So I want to say that even you can apply to molecular ion peak, but I can apply to fragment ion also, fragment ions. So here, but since M by M plus 1 is having one odd electron, this okay. After bombardment, they will give odd like this. So we have same molecular ion. Okay. So I will give examples here. So these are the rules for so even number of, if you contain even number of nitrogen atoms and odd, so and even number and even electron ion with and even number of mass nitrogen atoms will appear odd mass number. Okay, and even electron ion with even number of nitrogen will give odd mass number, and similarly odd electron ion with even number of nitrogen, or they will contain the nitrogen will be even number of nitrogen will be even, then they will give even mass number of 1 M by Z value. So this is about the fragment ions, and first case is for the molecular ion formation. So I will give more examples here. So for example, nitrobenzene or two nitro, so nitro NO2, or say metanitrobenzene, dinitrobenzene here. You can say 1, 2, 3, 4, 2, 4, dinitrobenzene. Okay. So when you say we got a bombardment, then we got this molecular ion, which have M by Z value. So around what almost will come this one. So let's say another fragment ion will get M by Z value will be around 2. We have 2 nitrogen atoms are even number, so even molecules. So here again here, okay, NO2. After bombardment, we got a molecular ion. Okay, so here molecular mass is given around 184. Okay, 184, and the M by Z value would also be 184. So that means here 2 nitrogen atoms are even number. So molecular ion will be even number, even mass number, M by Z will be even. So this is first case. So even will give even nitrogen number will give even number of M by Z value. So after fragmentation, when you fragment this one, even nitrogen after NO2. Okay, after fragmentation, so you will give lost this one, NO2 will be lost. So you can have NO2 will have M by Z value 46. So this 46 M by Z value 46. Single fragmentation will give M by Z46. So like this. So it's broken down here. So you go to 902. So fragment ions even will give more. Even will give this one. Fragment ions will give. This is wrong. Okay. So let's say M plus 1 because one hydrogen lost here. No nitrogen fast. Otherwise, there will be 2 hydrogen atoms. So we have to share even number of nitrogen atoms. So let's say one hydrogen radical is lost. Then you can have radical loss. Then we have some NO2. So one hydrogen is lost here. These are all hydrogen here, hydrogen here, hydrogen here. But one hydrogen is lost. So you can have this positive charge here. Any positive charge. Cation, no radical. So one hydrogen radical. Then M by Z value will be one loss means 183. So what I want to say that I'm repeating again. Okay, here the one electron or electron here. This is one electron having 2 nitrogen atoms will give even or if you have or electron will give even mass number, or even mass number will give or electron like this. Okay, so this can be ruled. So here in the case only one permutation will give even will give or here even will give even. Okay, if the molecule is the nature molecule has contain even number of nitrogen atoms, then the M by Z value of the M plus ion will be even. On fermentation of this M by Z value, if the even will give the odd will give the even. Say suppose another one, say nitrobenzene NO2. So it has contained what number of nitrogen atoms. So after fermentation, so here M by Z around say 1, 2, 3. Okay, so it comes from nitrobenzene. Molecular mass is 1, 2, 3, 123. Okay, you can check also that. So here after bombardment we got a odd. So odd number of nitrogen atom will give M by M plus ion, molecular ion peak. Molecular ion peak will be the odd number. So when you lost this another fermentation, when you lost this will give NO2 having containing this will contain and nitrogen atom, or nitrogen should be always there. So it gives M by Z value will be almost will come and 12 and 36, 46. Okay, so mean odd will give even. So here even you odd. So here even will give the odd. So this is nitrogen. So I'm repeating again. Okay, past case is that the neutral molecules having even number of nitrogen atoms will give molecular ion having even number of M by Z value. Similarly, molecules having odd nitrogen atom will give molecular ions having odd M by Z value. So after fermentation, this M by Z value of the molecular ion after fermentation, single fermentation will give odd fragment ion. This is fragment ion. Okay, fragment ions. And similarly, odd will give even fragment ion. So you can like this. You can show. So then you can undergo further reaction. So you can undergo further reaction. So here further fermentation will go. So odd will give even will give odd like this. So these are the nitrogen rules. So today we lesson wind up here. So next class I will talk about the other classes of organic compounds. So today I'm talking about the fermentation. First one is the fermentation due to Maillard-Fortin rearrangement, and the second one is the fermentation due to nitrogen rule. So for Maillard-Fortin rearrangement, I'm just summarizing again to this. So in the case of Maillard-Fortin rearrangement, fermentation takes place by transfer of migration of gamma hydrogen followed by cleaving the alpha beta CC bond, okay, or carbon bond, beta carbon bond. So it is can have another one intense peak will give. So by giving this peak, we can say that the Maillard-Fortin rearrangement takes place. So I have given one example or to comparing this 3-methyl 2 pentanol, another one is 2 pentanol. So we compare this thing. So in the 2 pentanol, we got one peak at m by the value 58 due to the molecular property rearrangement. And second one is the fragmentation due to nitrogen rule. Here we have nitrogen said that even number of nitrogen molecules, having even number of nitrogen molecules, nitrogen atoms of the molecules will give even number of m by the value of the molecular ion. Similarly, odd number of nitrogen atoms of the compound will give odd number of m by the value of the molecular ion. So I am giving an example here. So, even number of nitrogen atom molecules will give even number m by the value of the molecular ion, and odd will give odd nitrogen atom of the molecule, and nitrogen molecule will give molecular ion having odd m by the value. And similarly, after fermentation, one single fermentation, odd even will give odd, and odd will give the even number. So this is about the nitrogen rule. So this is for today. Let's wind up our next class. I'll talk about the classes of organic compound.